This, in my opinion, is one of the most important and beautiful series in the whole of mathematics, and I am going to not quite prove it to you but give you a pretty good justification of it right now. So what does it actually say? Well, if we get rid of that sigma notation and show you what it's saying, it says e to the x equals, if n is 0, we'd get x to the 0 over 0 factorial, plus, then we'd get x to the 1 over 1 factorial, plus x squared over 2 factorial, plus x cubed. It's a nice little series, isn't it? It's a really simple one, plus dot 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 dot. So what it's saying is that e to the x is equal to 1 plus x plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, plus forever, which means that if we take just the first 3 terms, say, or 4, then we're not going to get e to the x because it goes on forever, but we're going to get a good approximation. But this is just so cool and weird. Why should a cubic be a really good approximation for an exponential function where the base of the exponential function is actually like a not even irrational, a transcendental number? And yeah, so this is pretty good, yeah? I'll show you a graph that shows these functions and them approximating e to the x. So these different graphs are the different approximations taking more and more terms as we go forward. So first of all, just 1 plus x, and then we go 1 plus x, and then we add on the half x squared, and then we add on the 1 over 6 x cubed, and so on and so forth. And you can just see from the graphs how quickly they start to really closely approximate e to the x, which is just brilliant. So where does this formula come from? Well, let's just start from the assumption, which is quite a big assumption, but let's say we hope we can write some e to the x as a polynomial. So a number plus an amount of x's plus an amount of x squareds plus, and we don't know how many of each, but that's our aim, is to approximate e to the x as closely as possible with a cubic and then more and more terms. Okay, let's say what happens, if this is true, what happens when x is 0? When x is 0, we would get e to the 0 equals, well, just a 0, wouldn't we? Because the rest of it's going to cancel because it's got x's in and the x's are 0. So actually, what we've got here is we found out what that first term would have to be, that a0. It would have to be a 1, otherwise it's not going to work. Okay, so gets us somewhere, doesn't it? 1 plus a1x plus a2x squared plus a3x cubed plus la 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 la. Okay, now this is the clever bit. We differentiate both sides. So the derivative of e to the x is e to the x, and on the right hand side we get a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus blah blah blah. And then we use the same trick. When x is 0, what do we get on each side? Left hand side e to the 0, right hand side a1. A1 is 1. We can keep doing this. E to the x differentiated again is also e to the x. Now we get 2a2 plus 3 times 2 a3x plus 4 times 3 a4 x squared plus blah blah blah. And then we can say when x is 0, well, e to the 0 would just be 2a2, and that's 1. So that gives us a2 is a half. Differentiate again. E to the x equals 3 times 2a3 plus 4 times 3 times 2 a4x plus all the other terms. Stick in 0 again. When x is 0, e to the 0 is going to be 3 times 2a3, which is 1. So that gives us a3 is 1 over 6, 1 over 3 factorial, 3 times 2 times 1, 3 factorial. And hopefully you can see that we could just keep doing this. We could just keep going. We could differentiate again. E to the x is 4 times 3 times 2a4, and then what we'd have as the next term is 5 times 4 times 3 times 2 x, and then the next one will be 6 times 5 times 4 times 3 x squared, because the 6 and the 5 and the 4 and the 3 would have come down, but not yet the 2, and then you can put in x is 0, and then you get e to the 0 is, all these terms cancel because they've all got x in, and you get 4 times 3 times 2, which is 4 factorial a4, and that is equal to 1, so a4 is 1 over 4 factorial. And this you can see, it's not a proper proof, but hopefully you can see the justification for saying that an will always be 1 over n factorial, and then that gives us the series e to the x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4 plus blah blah blah. A very important and very beautiful infinite series.